Okay, so it feels like you really can't go a day anymore without, interacting with some kind of intelligent system.
Right. They're everywhere.
Yeah, from like the movie recommendations you get
Yeah.
to all the stuff working behind the scenes online, it feels like magic sometimes.
It does, but there's definitely a method there. A lot of thought goes into how these things are actually built.
And understanding the basics, the design ideas, it's not really about becoming an AI coder overnight or anything.
No, not at all. It's more about getting a useful perspective, right?
Yeah,
How they work, what they're good at, maybe where they fall short. And you don't need to get totally lost in the technical jargon either.
exactly. Which brings us perfectly to what we're doing today. One of you listeners sent in this fantastic collection of notes, articles, all about intelligent agent architectures and design principles.
Yeah, great stuff.
So our mission basically is to unpack all that, look at the core concepts, explore the different ways these agents are put together, and really get a handle on the key things to think about for making AI that actually works well.
Consider it the express lane to understanding this stuff.
Right. So where do we start? Maybe with the absolute basic building block, the agent idea itself.
Good plan. So in AI terms, what is an intelligent agent?
Well, think of it like this. It's basically some entity acting on its own, autonomously.
Okay.
It lives in some kind of environment. It can sense things in that environment using sensors, obviously, and then it acts on the environment using actuators,
Yeah.
all to achieve some goal.
Like a self-driving car.
Perfect example. Cameras, LiDAR, those are its sensors. Steering, braking, those are the actuators. And the goal, getting you safely from A to B.
And what's really useful, think about it this way, is how the agent concept works as an abstraction, a high-level idea.
How so?
Well, it lets you focus on the big picture first, right? What the agent does, its goals, how it interacts with its world, before you get bogged down in exactly how its internal circuits are wired, so to speak.
Right. It's like saying, this thing needs to see and move way before you argue about whether it uses simple rules or some complex neural network.
Exactly. And the notes you sent really emphasize this. It makes designing complex systems much more manageable. You separate the what it does from the how it's built.
The job description versus the blueprint.
Nicely put. And that blueprint idea leads us straight into the main types of agent architectures. The sources lay out 4 big ones.
Okay, let's walk through these blueprints. First up, logic-based architectures.
Yeah.
What's the core thinking here?
Okay, so logic-based. Think. Think like a detective. Its behavior is driven by logical reasoning.
Okay.
It has a knowledge base, facts, and rules written in formal logic. It gets new info, uses rules of inference to reason about it, and then decides what to do.
So it's using tell, ask, perform, adding facts, asking questions, doing actions.
That's the core loop, yeah. Add new info, query what it knows, act based on the logical conclusions.
Right. Sounds very precise. What are the upsides and downsides?
Well, the big strength is clarity. Because it's formal logic, everything's unambiguous. Clear semantics, as they say.
Like if light is red, then stop.
Yeah.
Very clear.
Exactly. And that means you can often formally verify its behavior, prove it'll do the right thing in certain situations. It's great for well-defined problems where you have all the info and clear rules. Plus, it's often transparent. You can trace the logical steps.
That sounds incredibly useful. So why aren't all AIs built this way? Must be a catch.
There definitely is. Mainly, logical inference can be really slow, computationally expensive, tough for real-time decisions in fast environments.
Okay.
They also tend to be brittle. They struggle with uncertainty, incomplete info, things not explicitly in the rules. The real world is messy, and it's hard to capture all that in rigid logic.
Right, the brittleness. That was a big push towards other approaches, wasn't it?
Absolutely. And they don't always scale well. More knowledge can mean much slower reasoning.
Okay, so maybe not ideal for, say, a robot navigating a busy street. But are they still used?
Oh, definitely. Just maybe not as the whole system. They're often used as components within bigger hybrid systems.
Ah, makes sense.
Yeah, because their strength in explainability and verifiability is still really valuable. Like, you can use a logic module to check if an action violates safety rules.
Using the right tool for the job. Okay, cool. Let's move to the next blueprint then. Reactive architectures. Sounds like the total opposite.
It pretty much is. Reactive systems kind of ditch the central planning and deep reasoning. It's all about a direct, real-time connection, sensor input, straight to actuator output.
Like a reflex.
Kind of, yeah.
Yeah.
The overall behavior just sort of emerges from simpler bits reacting to what's happening right now. Think about swatting a fly or how a bug darts away from light. Immediate reaction.
So no complex internal world model or thinking ahead.
Generally, no. The classic example is Rodney Brooks's subsumption architecture. It uses layers of simple behaviors, often built with something called augmented finite state machines.
Augmented, meaning?
Basically, state machines with a bit more memory or simple computation within states. Just enough for slightly more complex reactions. But the key idea is subsumption.
Subsumption.
Higher layers can override or subsume the outputs of lower layers. So an avoid obstacle layer might suppress a move forward layer if something's in the way.
Ah, okay. Like priorities.
Exactly. And this was a big deal because it showed complex-looking behavior didn't always need complex internal representations. It shifted focus to how the agent interacts with its environment.
That sounds super fast and efficient then. What are the main pros?
Speed is definitely one. Great for dynamic environments because they react instantly. They're robust too because they're always dealing with the now. Plus, usually cheaper computationally and easier to implement for simple stuff.
But I bet the downsides and the flip side of the logic-based ones.
You got it. They struggle with complex, long-term goals that need planning. Learning is limited. And because the behavior emerges, it can sometimes be hard to predict exactly what it'll do or to debug it.
Yeah.
And yeah, usually no significant internal state or memory.
It's just fascinating how this reactive stuff, challenged the old symbolic AI, showing intelligence, like in those early robots, could just bubble up from simple interactions.
It was revolutionary. Brooks really argued intelligence wasn't just in the brain, but in the whole embodied system interacting with the world.
Mind-blowing, really. Okay, third architecture, belief, desire, intention, or BDI. This one sounds more human.
It definitely tries to be. BDI models intelligence using these mental attitudes, beliefs what it knows, desires what it wants, its goals, and intentions, the goals it's actually committed to pursuing with a plan.
Inspired by how we think and act.
Pretty much, yeah. Inspired by philosophical models of practical reasoning. You might see BDI ideas in, say, sophisticated planning tools or virtual assistants that try to anticipate your needs.
So how does it work day to day or moment to moment?
It's usually a cycle. Perceive the world, update beliefs, look at desires, what goals could I chase, then deliberate, form intentions, commit to specific goals, then figure out a plan and execute it.
And that commitment part is important, right? The sources mention that.
Absolutely crucial. Based on Bratman's theory, if an agent constantly reconsidered every possible goal based on tiny changes, it would just dither. Commitment provides stability to actually follow through on plans.
Makes total sense.
Yeah.
You'd never leave the house if you constantly reevaluated whether you really wanted that coffee.
Yeah.
So, strengths.
Well, it's intuitive. It mirrors human reasoning, which can make it easier to design and understand. It's good for complex planning and goal-driven stuff, and it clearly separates knowledge, motivation, and commitment. Plus, that balance between thinking and doing via commitment.
Sounds powerful. What about the challenges? Seems like it could get complicated.
It can be. Implementation is complex, especially keeping beliefs, desires, and intentions consistent as things change, and there's computational overhead for deliberation and planning. Plus, classic BDI doesn't really have built-in learning.
Okay, so good for strategic thinking, but maybe needs help with learning or super fast reactions, which I guess leads us nicely to number 4, layered or hybrid architectures, trying to mix and match.
That's the goal, exactly. Get the best of different worlds. Combine, say, reactive speed with deliberative planning.
To balance things out.
Right. Leverage the strengths of each approach, cover the weaknesses. Get an agent that's both responsive and goal-oriented. A lot of current research focuses here, realizing there's probably no single best architecture for everything.
So how do they structure these hybrids? What do the layers look like?
Often you'll see a reactive layer at the bottom for quick responses, then maybe a deliberative layer on top for planning and complex decisions, sometimes even a meta management layer overseeing the whole thing.
Okay, and how do these layers talk to each other?
The notes mention 2 main styles: vertical, where it's hierarchical, the planning layer sets goals for the reactive layer. Interap is an example.
Right.
Or horizontal, where layers work more in parallel, maybe proposing actions, and a controller decides which one wins. Turing machines is like that.
So it's about making the different brain parts cooperate effectively. What's the big win with hybrids?
The main advantage is getting that balanced capability set. Quick reactions when needed, but also strategic planning for the long haul. They're flexible and can be efficient, using simpler layers for routine stuff and saving the heavy computation for when it's really necessary.
But I imagine coordinating all that isn't easy. Potential downsides.
Definitely. Designing how the layers interact is tricky. You need smooth communication and ways to resolve conflicts if Say the reactive layer wants to dodge left, but the plan says go right.
Yeah, that sounds
It
complicated.
adds complexity to the design, debugging can be harder, and sometimes there's performance overhead from the coordination itself.
Okay, phew. So those are the four main architectures. But you mentioned the sources also distinguish between architecture, function, and program. Can we unpack that a bit?
Yeah, this is super important for clarity. The agent function, that's the abstract ideal. What the agent should do, it maps the entire history of what it sensed to the action it should take now. It's the what.
The theoretical perfect behavior.
Exactly. Then the agent architecture. That's the blueprint, the structure, sensors, actuators, knowledge base, reasoning engine, how it's actually put together, the how in terms of design.
Got it. Blueprint.
And finally, the agent program. That's the concrete code, the algorithms, the data structures that run on the architecture to implement the function, the how in terms of actual code.
Okay, so function is the goal, architecture is the plan, program is the build, like your library analogy earlier.
Precisely. And remember, different architectures, different blueprints could be used to build that same library to achieve the same function, but they'd have different characteristics, costs, maybe different speeds of access.
Makes sense. Now, why is picking the right architecture such a big deal then? It sounds foundational.
It's absolutely pivotal because that choice dictates everything. How the agent sees the world, how it thinks, how it acts. It's not just a tech detail. It's like a commitment to a philosophy of intelligence for that agent.
Wow, okay.
It directly impacts things like reactivity, how fast it responds. Proactiveness, does it take initiative? Rationality, how good are its decisions? Can it learn? How efficient is it?
So different architectures suit different jobs.
Totally. You wouldn't use a purely reactive design for financial forecasting, probably. And maybe not a super deliberative one for basic obstacle avoidance. Choosing wisely avoids building something that's just wrong for the job or gets stuck spinning its wheels.
Okay, so regardless of the overall architecture style,
Yeah.
are there common pieces, core components you'd expect to find in most agents?
Yeah, definitely. While the specifics vary, you almost always need a sensor interface to get data from the environment,
The world,
an actuator interface to do things in the world,
the world.
some kind of knowledge base or internal state. It's memory, basically, for context.
Remember things.
And, of course, a reasoning or decision-making engine to process info and choose actions.
The brain part.
Kind of, yeah. And increasingly, you see a learning element as core, too. Agents need to adapt.
Right, learning seems key nowadays. Okay, so those are the parts. But the sources also talk about broader design principles, things you need to keep in mind for making agents effective. What are those?
Yeah, beyond just the architecture, these principles are vital. First, modularity. Building with distinct, manageable pieces.
Makes sense. Easier to build, test, fix, change. Like building with Lego bricks instead of one solid block.
Exactly. Think of a chatbot. Separate modules for understanding language, managing the chat, finding answers. Then scalability, can it handle more work, bigger environments, without falling over?
Like a fraud detector needing to process more and more transactions.
Precisely. Robustness and fault tolerance are huge, especially for real-world stuff. Can it cope with errors, weird inputs, component failures?
Critical for safety.
Right.
Like a supply chain agent needing to reroute if there's a storm.
Absolutely. Adaptability and learning, which we mentioned, improving over time, like recommendation systems getting better at knowing what you like.
Right.
Predictability and stability are important for trust. You want the agent's behavior to be understandable, consistent, though. There can be a tension there with adaptability, right?
Yeah, if it adapts too much, maybe it becomes unpredictable.
It's a balancing act. Then, explainability and transparency, XAI. Can humans understand why it made a decision? Crucial for trust, accountability, debugging. Some architectures make this easier than others.
That makes sense.
And finally, security and privacy. Protecting the agent, protecting the data it uses, super important, especially with sensitive info like healthcare data. Agents can open up new security risks.
That's a lot to juggle, and they all seem connected.
They really are. And you often have trade-offs. More explainability might mean less raw speed, for instance. It's about making smart choices for the specific situation.
Okay. Now, another tool the sources mentioned was the P framework, PEAS. What's that about?
PS. It's a really handy way to nail down the agent's job description and context before you start designing. It stands for performance measure, environment, actuators, sensors.
Okay, break it down. Performance measure. Yeah. That's how you keep score, right? How you know if it's doing well.
Exactly. What does success look like? For the self-driving car, safety, speed, legal driving. For a spam filter, catching spam, not blocking real emails.
Got it. Environment. where it lives and works.
Yes, but more than just the name. What kind of environment? Physical,
Okay.
virtual, static, dynamic. Fully observable, or can it only see part of the picture? These details really matter
Why do they matter so much?
because they dictate the challenges.
Hmm?
A dynamic, partially observable environment is way harder than a static, fully known one. It heavily influences what kind of architecture and capabilities the agent needs. A dynamic world might push you towards reactive components, for example.
Right. Okay. Actuators, that's how it acts.
Hmm.
It's hands and feet, so to speak.
Precisely. Motors, wheels, grippers for a robot, displaying things, sending messages, changing files for a software agent.
And sensors, how it perceives things, its eyes and ears.
You got it. Cameras, microphones, thermometers for a physical agent, reading files, network packets, system clocks for a software one. Doing a thorough P's analysis up front is just critical.
So you really understand the task, the world, the tools it has before you choose the blueprint.
Exactly. It tells you what capabilities are needed, what sensors and actuators are essential, and which design principles might be most important. Safety-critical environment, robustness, and explainability jump up the list.
Makes perfect sense. Okay, one last big thing. The source is really hammered home. Simulations. Why are they so indispensable?
Oh, simulations are fundamental. You basically can't develop complex agents without them. They're your controlled testing ground.
A virtual world to play in.
Pretty much. You can test things repeatedly under controlled conditions in scenarios that would be way too expensive, dangerous, or just plain impossible in the real world.
Like testing a Mars rover before you actually send it to Mars.
Exactly. Or testing algorithms for autonomous vehicles without risking crashes on real roads. They let you rapidly try out different designs, compare architectures, tweak parameters, and see what happens.
And understand weird emergent behavior.
Yes. Sometimes complex systems behave in unexpected ways. Simulations let you explore that safely. The notes mentioned great examples using reactive simulations for traffic flow, BDI for emergency response like Fire Chopper, hybrids, and RoboCup soccer.
So it's not just for final checks.
No, not at all. It's an active part of the entire design loop. You design, simulate, analyze, refine, simulate again, constantly checking against those P's criteria, making the agent better and better before it ever touches the real world.
Wow. Okay, this has been genuinely illuminating, a real deep dive. Let's try and recap the highlights.
Right.
We started with the agent concept as a useful abstraction, the four big architecture types, logic-based, reactive, BDI, and hybrid, each with its pros and cons.
Right, the different blueprints. And the key difference between the abstract function, the architecture blueprint, and the actual program code.
And why choosing that architecture is such a crucial first step. We talked about the common parts, sensors, actuators, memory, reasoning, learning.
And those vital design principles guiding development: modularity, scalability, robustness, adaptability, explainability, security, ethics, all that.
Plus the P's framework for understanding the agent's world up front.
And the absolutely essential role of simulation all the way through.
It really pulls back the curtain on how these intelligent systems we interact with are put together.
It does. And it makes you realize that even seemingly simple things like recommendation engines have these kinds of architectural choices and trade-offs behind them.
It definitely makes you think differently about the AI you encounter, doesn't it? Like, what approach are they using? What were the designers prioritizing? Something to ponder as we navigate this increasingly intelligent world. Thanks so much for breaking all this down.
My pleasure. It was a great discussion.